Okay, so today I'm going to be discussing point groups. I'm going to be discussing why are they important, some examples of different point groups and how they can be used, and why in general in inorganic chemistry they can be useful. So first off, what is a point group? In essence, what a point group is just a set of symmetry operations we give to a specific molecule. They describe the molecular geometry. We've already seen some different type of symmetry operations, including a C, D, S, and basically this was just a warm-up for telling us what point groups are. So, why do we need to know this? What is so important about a point group for inorganic chemistry? Well, when we're able to find out the molecular geometry of a molecule, it provides info about how the molecule behaves. And this is really important to inorganic chemistry when we start looking at different, more complex molecules that may include, different transition metals. And what we're going to find out is that there isn't just like, say, one different point group. We are going to find out is that there are many different point groups and that they can all look incredibly different. Some can be incredibly complex, others not so much. And you know what? I am going to, with my eraser, there it is, just go over some different point groups and what they represent. So we can start with the easiest one, and that is CS. What is CS? Well, basically, all CS is it's the most simple type of point group. What does it mean? It has specifically two elements that make it a molecule. One being the simplest is identity, or E. And all we know about that is that if you rotate it around 360 degrees, it'll be the same as it came back. And that's true for every single molecule out there. It also has another thing known as a reflection plane. So essentially, you can split it in half and it'll look the same on both sides. That's the same horizontal as it is vertical. One example of this is, give me 1 second to find the name of it. Give me 1 second. Sorry about that. Ethylene. Basically, you can have a bromine attached to a carbon with a methyl group, double bonded to that. A Cl is attached, a chlorine's attached with another methyl group. So, how does this work? It has an identity in that you can rotate this 360 degrees. It's still going to be the same molecule. We also have a reflection plane. Now, this reflection plane, while it might not be obvious, is in the horizontal direction. Because this is a, because this does not have any molecules coming in or out, we're able to essentially split it in half and have it look the same. And this is just the one example of just the easiest molecule or most simple form of the molecule. And we go into other different point groups, there's CI, and it's the same thing as CS. The only difference is there's an inversion center. And an example of that would be, sorry about that. Trying to find a good example of what this could be. Well, Br to Cl2. Ethane, sorry. So we have a molecule here. We can say have a methane group coming out, or a methyl group coming out. You can have a bromine on the side and a chlorine. Same thing here. You can have a bromine, chlorine, say a methyl group coming out. And basically all an inversion center means, if we take this, let me redo this actually. So chlorine here, and yeah, that's better. So basically all an inversion center means is that we can take one molecule from here and reflect it back over here. That's the same for bromine, as you can see, that's in the middle, and same for the methyl group. And you know, as we go on, we find out they're more complex molecules. So we can say have something like a C and V, and what this shows is that, true for all molecules, it has an identity. And it also has a principal axis. Now its principal axis, as we've seen, can be up to C2, maybe it's C3, maybe it's C4. Basically, C and N being the amount of integers of where it can rotate. And last but not least, we have the V here. Now, what the V represents is it means it's it has a vertical plane, a vertical axis in which it can be turned. So, what would be an example of this? Well, you have bromine, or bromine trifluoride. So, usually we'll start with asking ourselves all these questions. So, can we rotate 180 degrees? Well, of course, every molecule has that. But now, when we get to the question of what's the principal axis, well, we just need to see how this can be turned around. You know what? Actually, give me 1 second. This might not be a good example. Sorry about that. This is better, actually. This is a better example because, well, I'll show you in a second. So, identity, yes, is that the principal axis is C3. What that means is basically we can rotate it around, I think, if I can remember correctly, I think it was 180 degrees. Right, and it'll look the same. There's also a C2 axis where we can rearrange these molecules, but notice, C3 is greater than C2. So because of that, C3 is going to be the principal axis here. And once we get to this, we start asking ourselves some more questions. Some of those questions include, you know what, sorry about that. I messed that up again. Okay, so best example for this, ammonium. Sorry about that. Okay, so C3 axis, principal axis, we know this. Now, to get to the next question being, 1 second. Question after that usually, and I didn't show that here, but the question we ask is, are there any C2 axes that have the same number as the principal axis. Basically what that means is n, whatever n is for this molecule, which is 3, are there as many C2 axes with that? So for this one, we're asking ourselves, are there 3 C2 axes perpendicular to the nitrogen? The answer is no. We can rotate here, we can rotate here, but that's about it. There's only 2 really. So after that, we ask ourselves, is there a, not a vertical, but a horizontal reflection plane? And the answer is no, because if we rotate around this, it's going to look completely different. So for that, we say no. So what makes this CNV is the fact that it has instead a vertical axis. We can flip it around any which way, and it will look the same. So that makes it CNV. It appears I'm going over my time limit, but you know, these are just some examples of different point groups we can have. When it gets to more complex molecules, we can say something that's tetrahedral or octahedral. But these are just some few examples of different point groups, what they mean in inorganic chemistry, and how they can be used properly.